Hello and welcome to another one of D's ADD videos. Today we're going to look at the concepts of titrations. What is a titration? In this case we're going to be looking at acid-base neutralization reactions. So the titrant is what you're dropping into what's being titrated, and it can be either acid or base in one and the other would be in the beaker. Okay, so if I had acid in red here, then the base would be in the beaker, or vice versa. So, to refresh your memory on a neutralization reaction, the general concept is acid plus base gives you salt plus water. And there are two types we're going to look at. The first type is going to be a strong-strong interaction, and the second type is going to be a strong-weak interaction. But in both of the types, there's going to be important times during the titration we're going to look at. We're going to try to find and look at the pH before it begins. We're going to find it during the titration at different times after different amounts of titrant have been added. Now there is a specific one during strong weak that we'll address later at halfway to equivalence point. Something special happens. Okay. pH will end up equaling pK, and I'll go through why that is later on. And then at equivalence point here, what's happened is all of what you had in your beaker has been neutralized. So now we're left with the conjugate. And that will make sense here in a little bit. Just kind of try to see the big picture. And if we started with Kas and the acid in the beaker, after the equivalence point it would be Kb's because it's the conjugate, and vice versa. Okay? So, how are we going to handle these? For strong-strong, what you're going to do is you're going to find moles of each first. Or actually, I'm sorry, I apologize. If we're doing before the titration for strong-strong, you should remember a strong acid or a strong base, like HCl, concentration equals the proton concentration, because it's 100% dissociated. And then the same thing would be for KOH, concentration of the hydroxyl ion. So you just can do the negative log of this to get the pH, or the negative log of this. So if you remember, if you did this one, that would be your pH right away. And if you did this one, you would end up getting POH, and you would need to do 14 minus answer to get pH. Okay, but during the titration, we have neutralization going on, so you would need to find moles of acid and moles of, actually, let's do it like this. Let's do moles of beaker and subtract moles of titrant. Okay, and what you're doing there is you're finding out how much did you neutralize. Okay, and then you will have moles left in beaker, and at that point what you do is you divide by the total volume, which is the volume of the beaker plus the volume of the titrant, and that will give you the molarity of what's left in the beaker. And again, if it's an acid, find pH by doing negative log of H, If beaker is acid, do the negative log of H. Because this is, even though this is the beaker, right? Beaker is strong. Strong equals proton concentration. Strong acid, like hydrochloric acid. But if the beaker is a base, then we have to do POH and then do the 14 thing again. Okay. That's basically it for strong. For a weak strong interaction, it's a little bit more complex. So step one for that one is going to be, if we're doing before the titration, you're going to have to do a Rice table. So you're going to have HA plus aqueous plus H2O liquid, which you don't need the liquid part. Alright, sloppy L. Gives me A minus. And this is, if I'm doing an acid, this could have just as easily been a base over here. And here we're going to get H plus. So this is the reaction. And then remember, initial change equilibrium. This should be some number that's given. Then this will be minus X. That's nothing. And then that would be nothing usually, X. So you end up with some number minus X there. And then Ka, the acid dissociation constant, if you remember from watching that video, is this. So that becomes X squared over the number minus X, and set equal to a known Ka value usually. So also there's that condition that states that if your Ka is 10 to the negative 5 or smaller, your initial concentration, whatever that molarity is going to be much greater than the change. So you can, so X is therefore is negligible. That means is this value right here, if Ka is 10 to the negative 5 or smaller, can just disappear, because that dissociation is so weak that it doesn't affect that initial concentration. So you just multiply over and square root, make your calculation much easier. Refresh your memory in product rule, because that doesn't, quadratic formula, because that doesn't always happen. So that's for before the titration. During the titration, however, you're going to use Henderson-Hasselbach equation, which pH equals pKa plus log of A minus over HA. Now, because these two are molarities and it's moles over volume and the volumes will be the same, this could also be plus log of Na minus and NHA. Okay. It doesn't have to be volumes, because the volumes would cancel out, right? If you remember, molarity is N of A minus over volume total, and then N of HA over volume total. And when you flip and multiply, these VTs cancel, leaving you that. Okay? And this brings up the point that I was making earlier at pH equals, at equal halfway, take 3, halfway to the equivalence point. That means I've added enough titrant to halfway neutralize what's in the beaker. These two values right here will equal each other, and the log of 1 is 0, and what ends up happening there is pH equals pKa, halfway to equivalence. Okay, and then at equivalence, what's going on here? We've completely neutralized whatever in the beaker. This might be my last video, I'm stuttering here. Whatever was in the beaker originally, we've completely neutralized. So now we have the conjugate. Since I've been dealing with an acid up until now, what would happen is I'd have the conjugate base now interacting with the liquid water, and this is aqueous. I forgot to put aqueous up there too, I think. This is liquid. All of the ones that are water should be aqueous. Oh no, I did remember. I did remember on the right side. Both of these are aqueous. And then here we're going to have the conjugate acid, aqueous plus, since that's a base, hydroxyl ion. So now we would be using KBs from here on in and trying to find out what POH is as a result and going from there. Okay? So make sure you check out the example. There will be an example video for both strong and weak strong, and there will be an acid and a base weak strong example. Okay? So the main thing is for you to watch those videos and then practice as much as you can. Once they become second nature, you will wonder why you thought these were so complicated to begin with. Alright? Thank you, and have a nice day.